What is the time? The singularity represents the end of time. Was it really the beginning of time?
But what is that? How can we understand that?
The universe is like a box. That's wrong. That's not the way that nature is. We're trying to understand this deep mystery. There are three fundamental forces of nature. It's about civilization. It's about knowledge. It's about how we progress as a civilization. Mathematics is a guide to the way that the universe works. All these ideas of symmetry and mathematical beauty are all in there.
Why it's called the particle of God?
Maybe it's one of the mysteries. We don't know is the most powerful phrase in our language.
So we are getting closer and closer and closer.
You'll get nowhere. If your goal is to understand everything, we are star stuff, or stardust, as he used to say. And it's true. The astonishing thing to me is that there are places in this violent universe which are so gentle that things like us can emerge on them. Mulțumesc. You can use that on You're recording, aren't you?
Omule, te salut, Dr. Mihail aici, un nou podcast BOABE de cunoaștere, după cum ai văzut, un podcast cosmic. Și înainte de a începe și de a plonja în tot ce înseamnă găuri negre, spațiu-timp, călătorii în timp, călătorii intergalactice, vreau să te gândești la acest sentiment pe care sunt convins că l-ai avut. Cu toții avem acest sentiment. Când ne uităm la cerul liber deschis noaptea și vedem stelele și ne dăm seama că asta e doar o infinită de mică părticică din univers, și ne dăm seama că nici pe aceea nu putem cuprinde și nu putem înțelege, avem acea senzație de neputință, de mic. Îți dai seama cât ești de mic și de insignifiant. Și te sperii și nu te mai gândești la asta. Ori adevărul e că ar trebui să ne gândim la asta. Și omul cu care vorbim astăzi este cel care ne inspiră să ne gândim la asta, să ne imaginăm lucrurile și să le înțelegem. Și nu degeaba, pentru că noi suntem făcuți din acele particule din acel univers. Când te uiți la stele, te uiți la locul din care tu provii și din care eu provin. Pentru că toate particulele care au masă, pe care le avem în corp, toate particulele de carbon, de exemplu, au fost forjate într-un soare imens care s-a încins la sute de milioane de grade Celsius și în felul ăsta particulele au aderat una la alta și au făcut această masă. Știu, este complicat, dar pregătește-te de lucruri și mai complicate. Despre ce înseamnă spațiu-timp, ce înseamnă călătorie în timp, despre ce înseamnă călătorie în alte galaxii și ce se întâmplă, de exemplu, dacă din greșeală ai cădea într-o gaură neagră. Despre toate astea vorbim cu Brian Cox. Profesorul Brian Cox este fizician de particule la Universitatea din Manchester, cercetător la CERN, locul unde s-a descoperit Boston Higgs, particula lui Dumnezeu. O să vedem ce este asta. Și este probabil unul dintre cei mai ascultați și iubiți oameni de știință care vorbește despre astrofizică, care este, îmi dau eu seama, una dintre cele mai frumoase științe fundamentale. De fapt, e știința fundamentală per se. E știința care te face să regreți că nu ți-a plăcut fizica, iar atunci când îl asculți pe Brian Cox, te îndrăgostești de fizică. Mulțumesc Unicredit Bank pentru faptul că sprijină podcastul BOABE de cunoaștere și iată, sprijină aceste inițiative educative și aceste călătorii în care, din nou, sunt șocat că l-am pe Brian Cox aici cu mine. Așa că hai să începem. Professor Brian Cox, welcome to BOABE de cunoaștere.
Thank you. And you taught me how to say thank you in Romanian.
Yeah, it's mulțumesc.
Mulțumesc.
Mulțumesc. Yeah, that's right.
Mulțumesc.
Yeah. So I want to say that I'm so incredibly glad that you came to our podcast and that I'm sitting here in the table with you. And I want to thank you because look, I was scrolling Instagram and I saw some reels about stars and I just liked them. And then your reels simply invaded my Instagram feed.
Invaded.
Yes. And I realized that I need this science to understand what we are made of and how life started. And after that, I started to read your books. This is the book I read recently. We have it in Romania. It's an excellent book. It's actually your first book. And I discovered after that Carl Sagan. And I'm reading Cosmos now, which is probably one of the best science books you can ever have.
It is. When I'm asked what's my favorite science book, I say Cosmos. And the reason is it's one of the first popular science books that I read. Yeah. And also one of the first TV shows that I saw, which was, there were 13 episodes of that show. 13 hours of astronomy in it was 1979 or 1980. And I still think today it stands up as one of the greatest science documentaries ever made. And of course, we've learned more since then. I mean, 1980. So in the live shows, I show images that Voyager 2 took of Neptune and Triton. That's 1989. So when Cosmos was written, we hadn't been to Neptune. So we hadn't visited all the planets in the solar system at that time. So things have changed. But for me, it's one of the first and one of the few science books that puts science in context. So it's not only about astronomy. It's about civilization. It's about knowledge. It's about how we progress as a civilization. So that's the thing that really I took from that. You know, I grew up with Carl Sagan. And a lot of the way that I look at the world now was formed, I think, by Carl Sagan.
Yeah, and that's amazing. Like the way I started to see things after watching your materials is that when you think about stars, it's not just stars.
Yeah,
it's not just some dead rocks somewhere. It's how life began in the end, and you start to understand where you come from, maybe where you're going. And you said like things changed since Carl Sagan wrote the book and filmed those TV series. And we were before recording, we were talking about your book, and you just said like, yeah, but I changed my mind about.
Well, it's not. So that's a book about special relativity, which is E equals mc squared.
Yeah.
No, I'm obviously the theory is the same, but I've changed a bit in the way that I think about it. So when you teach, so either write books or teach, and I teach special relativity at the University of Manchester now. To undergraduates. You just find different ways of not only explaining the science, but understanding it. And because relativity is, I think, a subject that you can continue to try to understand for your whole life, especially general relativity. We start talking about black holes.
Yeah.
And of course, that's one of the most interesting areas of current research. So they're not fully understood. So the implications of relativity and what lies underneath relativity. I mentioned it in the live show, actually. There's a field now called emergent space-time. The live show is called emergence. So,
yes.
So what is emergence? It's, in this case, we're saying that space and time may not be fundamental, which is not touched on in that book, in part because it wasn't as a popular field at that time.
You actually say, I made some notes, and you say the space, this is like a shocking, for somebody reading that for the first time, this is shocking notion that space is not fundamental. We don't have a space and we don't have a time. We just have like a web that is called space-time.
Oh, yes. So that's standard relativity.
Yeah.
We're now, from the study of black holes, beginning to think that space-time may emerge from some kind of network of qubits or something like that. But we can talk about that later. But in this case, you're right. So if you go back to Newton's laws, which 1687, so this is the first modern scientific theory, Newton's law of gravitation. And in there, Newton says that there is such a thing as absolute space. So he says it's an assumption. So it's how we probably think about it. The universe is like a box. Yeah. And there are places in the universe, and everyone would agree where those places are. And then time, he says that there's absolute time. It's like there's just a clock that ticks, and it would be God's clock or whatever it is, but everybody agrees on the time.
Ticks like the same way everywhere in the universe.
And so everyone would agree what time it is and what, and that's wrong. That's not the way that nature is. So this was Einstein's great realization in 1905. He was actually forced into it by work in electricity and magnetism from the 19th century. So in 1905, we get the special theory of relativity, which says, as you point, there's no such thing as absolute space. There's no such thing as absolute time. There is a property, which is the distance in space time between events, which everyone agrees on with the things that happen. But that was the Great Revolution in 1905, which led to E equals mc squared and all those things.
Yeah, but for somebody that is listening now, let's say the result of that, and I was thinking about that in the plane I was flying this morning, is that while I was traveling in the plane towards you, you were like sleeping in Copenhagen. Yeah. I was flying with this.
I was partying. I was out. It's rock and roll, you know. I was in a bar.
So you were in a bar, but you were standing in the bar. Yeah. And I was flying towards you. And that means that we were experiencing time in a different ways, right? I mean,
yes,
time was a little bit diluted for me, right? Dilated.
Yeah. So the time, essentially, a way to think about it in relativity, the way that I like to talk about it now, is that, so you imagine this tabletop, and it's a map of space and time.
Yeah.
So we've lost 2 dimensions of space here, but forget about that. So we've got space and time, and you have things that happen, which you could draw on a map. So the things like you were on the plane, you click your fingers.
Yeah.
We call that an event, something that happened in space time. So
Yeah.
you can say there it is. And then there's the event now when we meet. And so we say, well, what's the time difference? You would have, if we'd synchronized our watches, then you would say, well, at least we'd agree on the difference in time between you clicking your fingers and us meeting now.
Yeah.
But actually, the simple thing, the best way I think of thinking about Einstein's theory is that what is the time? The time you can think of as the distance over space-time, the distance over the map between 2 things that happen.
Yeah.
Well, if I say what's the distance between Bucharest and Copenhagen, you would rightly say, well, it depends on the route. That obviously it depends which way you go. It's the same here in space-time. But the distance you travel over space-time is the time you experience along that route. So if we take different routes between 2 things that happen, as we did right there, then you will measure different times on your watch, because the time is measuring actually the distance that the watch travels over the map.
Yeah.
That's it. That is it, actually. That's the central idea in relativity. When you put it like that, the time on your watch is the distance your watch has traveled over space-time between things that happen. Then you realize, well, you can take different routes. And so you measure different times between things that happen.
Yeah.
That's it. I mean, there isn't anything else to it, actually. So it's actually no more complicated than saying there are different routes between cities. There are different routes between events. Depends how you get there.
We can keep that in mind, because we're going to get there when we're going to talk maybe a little bit about traveling at near the speed of light and what happens then, because there's where magic, in our view, happens. But if we get back at what you're doing, you're a particle physicist. Yeah. So for somebody that doesn't know that, like me, what's you're teaching? What are you doing professionally?
So I started out actually doing astrophysics at the University of Manchester, and I moved into particle physics through studying supernova explosions. So supernova explosions are stars at the end of their life, massive stars that run out of nuclear fuel, collapse and explode. And they can leave different things behind. Some of them leave black holes behind. Some of them will leave these neutron stars behind, pulsars and so on. But there are particles that come out of supernova explosions, a weird kind of particle called a neutrino, which are really unfamiliar to us. They're a central part of the way the world works. They're intimately involved in nuclear reactions in the cores of stars, but they interact extremely weakly with the stuff that we're made out of, normal matter. So there's a number that I say in the live show, actually, that from the nuclear reactions in the sun, at the moment, at now, there are something like 70 billion neutrinos per centimeter squared per second going through your head from the nuclear reactions in the sun.
Like right now when we're listening, yeah.
And the overwhelming majority of them go straight through the Earth.
But what did they? I have
So
read about them.
They're one of the fundamental particles.
They have mass?
They have a tiny amount of mass.
But how did it happen? Like, if they have mass, why don't they stop in another mass?
Because they only feel one. Well, they feel gravity as well. But putting gravity aside, there are 3 fundamental forces of nature. This thing called the weak nuclear force, the strong nuclear force, and electromagnetism. So electromagnetism is the familiar one to all of us, right? It's motors and generators and magnets on your fridge door and things like that. So that's electromagnetism. The weak and the strong nuclear forces operate in the nucleus. primarily. So the strong force sticks the constituents of protons and neutrons together, and then sticks the protons and neutrons together in the atomic nucleus. That's the strong force. The weak force is, if you're watching it and you've done a bit of physics, then it's radioactive beta decay and things like that. So certain radioactive decays are the weak force.
Yeah.
But it's very, very, very short range. And the neutrino only feels the weak force. And so it's really short range. So it means the neutrino has to go really close to an electron in your body or a quark in the protons or whatever it is in order to bump into it. It just basically misses everything. So you're transparent to neutrinos, and the Earth is pretty much transparent as well. So they just go all the way through. The reason the weak nuclear force is short range ultimately leads you to the Higgs particle and the Higgs boson and all those things that we did at the Large Hadron Collider.
We're going to talk about that because it's also called like the God particle, right?
Yeah, but that's the answer. So the answer is I went to particle physics through that.
Okay,
and particle physics is the study of those. One way to think about it is the study of the fundamental building blocks of nature and the forces that stick them together.
And you study that, and you've mentioned CERN, and for somebody that doesn't know what happens there, what are you studying there, and why do you need such a big circle for accelerating what?
So the Large Hadron Collider at CERN is 27 kilometers in circumference. You think of it as a vacuum tube. They're about that big, right? These little vacuum pipes that go around underneath some France, mainly France, and a bit of Switzerland at the top. And what we do is we accelerate protons around to 99.999999% the speed of light. So they go around 11,000 times a second.
Speed of light.
Very close.
Okay.
So they go around 11,000 times a second, and we collide them. So we make these very high energy collisions. So the thing we're interested in, really, there are different ways to think about it, but one way is we're interested in these very high energies. These are energies that were last seen naturally in the universe, very close to the Big Bang. So you're looking at the way that physics, the universe behaves in the earliest moments. That's one way to think about it. Another way to think about it is, so you've got this book, E equals mc squared. So that says energy can be changed into mass. So there are very massive particles in the universe. One example is the Higgs boson, for example. So how do you make a thing? If you want to make one of those things, they don't get made in this room, right? As particles, there's not enough energy there. So you can essentially these particle accelerators deliver a lot of energy into a very small space. So you can make heavy particles and you can observe them and see how they behave and measure their properties. And so that's one of the things the Large Hadron Collider does. Famously, it makes Higgs bosons. So we can see these things, and they were predicted back in the 1960s for reasons we can talk about later if you want. So various theoretical ideas. But 50 years later, we needed this amount of energy to test that theory to see if this guess, right, which is what a theory is, was correct. And it turned out it was actually correct, the guess from the 1960s.
And you actually were there, in
2012, yeah.
2012, you were there at the discovery of this particle.
Yeah, I mean, we obviously over the few years before that, we'd started to see these things. The particle physics is quantum mechanics, right? And quantum mechanics is a probability theory. It's like tossing a coin. So you have to see a lot of things. You have to make, you never know, for any one particular thing that looks a bit like a Higgs particle or looks like a Higgs particle, you can't just say, oh, we found it now. You need to you have to have a lot of them. You have to get, it's like tossing a coin and saying it comes up heads 3 times. So you say, is the coin a fair coin, right? You don't know if you only toss it 3 times. There's a reasonable probability it will come up heads. If you do it 1,000 times and it comes up heads 1,000 times, you can say, yes, there's something wrong with this coin. Particle physics is like that, really. So you have to make a lot of these things. And so over the years, we collected enough that we were absolutely sure that we'd seen the signature of this new particle, which was the Higgs particle.
And how does it help us, like, that we discovered? What did it bring new for somebody that doesn't know like a lot about physics? How does it help us, and why it's called the particle of God?
Well, I mean, actually, it was called The Particle of God because a book publisher, it was a very famous physicist called Leon Lederman, who had a book on particle physics. He's a Nobel Prize winner. And the way that he tells the story, his publisher called it that, and he didn't like it very much, but it was a good title. So it's nothing to do with God.
Okay.
It's just some book publisher thought it was a good idea. But it stuck, right? It's a nice name. It's a different kind of thing to the other particles that we've talked about. So we talked about these things that make up protons and neutrons, and the neutrinos and the electrons would be another example. This thing, the Higgs particle, is really fundamentally different. So there are different ways of thinking about it, but my favorite way currently of talking about it is that it's about this weak nuclear force again. So we talked about the weak force.
Yeah.
And I said the reason all these neutrinos miss your head, 7 billions of them going through your head, and you don't get a headache, is because it's very short range. Why is it short range? Well, it turns out that is the answer. The Higgs particle was kind of invented, really, theoretically, to give an answer to that question. And it's really fascinating. And it's partly, my favorite way at the moment is, do you know superconductors? So there are these things called superconductors which don't have electrical resistance. So you can build these remarkable magnets that have no resistance, and they're powerful magnets. So the universe is a bit like, it's like we're living in a superconductor. And what the Higgs field, this Higgs thing that permeates the universe does, is it allows that force, or makes that force short range. And it's very analogous to the way that electricity and magnetism work inside a superconductor, basically. So it is part of the explanation for why this force is short range. But another way of thinking about it is it's often presented as it gives mass to the fundamental particles.
Yeah, that's what they wrote in the book. Yeah. In
the theory that we have, it gives mass to the things that carry the weak force, and that's really the essence of the thing. That's why it was invented, because we had all sorts of problems with describing this weak nuclear force. It's a kind of mysterious force, behaves in a strange way. So it was there. Now, in the theory, it also gives masses to the quarks, and it gives masses to the electron. That's kind of in a way, kind of a side issue, I think. That the real interest in it is this description of the weak nuclear force. And the way that I like talking about it now is that it is like that we live inside a giant superconductor. So it's almost like we're fish. I think Frank Wilczek, the great Frank Wilczek, who got the Nobel Prize for one of these forces, the strong nuclear force, he describes it as, I think he says it's like we're fish, right, swimming in this ocean, in this water. Yeah. And we don't really know in everyday life. We don't think about the water. I suppose a fish doesn't know about the water, right? It's in it. It's like that. We're in this giant, Frank Wilczek calls it a giant multicolored superconductor that we live in. It's a really beautiful analogy. So the Higgs is part of this, it's something that exists in the universe, a fundamental part of the reason our universe is the way that it is.
That's called also Higgs field, or?
Yeah. So
it's like a field we're swimming in. And this field is like giving us mass, right? It stops us.
There is an analogy which is often used. It was a very old analogy, which was famously used in the UK, actually, in Britain in the 1980s to convince politicians that give us the money for the Large Hadron Collider. But so you can think about it in terms of wading through this stuff. And if it's like this kind of thick fluid or something, you're slowed down.
Is that a correct analogy?
Well, different particles interact with it in different ways. So it's kind of slightly different to that. Some things like the light, particles of light, photons, don't talk to it at all. So they just go at the speed of light through it. So they're unimpeded by this thing. Other things interact with it by different amounts. And that you could think of it as kind of giving them mass or slowing them down. There are different analogies. The thing I would say about the Higgs is it's absolutely stunning. The mathematics of the theory that was developed in the 1960s and 70s is just remarkable and beautiful. And it's very deep and it's very elegant. And it's all, I talk about in the live show a bit, it's about symmetry. All these ideas of symmetry and mathematical beauty are all in there. And it's almost as if I've come to think that almost any analogy doesn't do it justice, really. It's such a beautiful bit of physics. And I remember seeing Peter Higgs interviewed on this, saying this a similar thing. He's saying that you can give these analogies. None of them are very good, actually, these analogies. So over the years, I've gone, I don't know what the right analogy is. I think the thing about superconductors, right? So this idea that you can have these materials that don't have any electrical resistance. So currents can just flow forever in these things. And they also stop the force, the electromagnetic field going into them. So that they have this behavior that shields the interior from the force. And one way of looking at those is that the photon, so the particle of light, you can express that as they get a mass. They don't go very far, so they don't go in to the thing. And so you get this short range behavior. And it's very analogous to that, actually. So it is, I think Frank Wilczek's right, that it's as if we live inside a superconductor. Well, not as if, we do live inside this weird superconductor. And it's a really cool thing, actually, but it's so hard. I think that's one of the things about physics, theoretical physics at this level, is it is astonishingly beautiful. That and ultimately your access to it is it just you need to get around the mathematics ultimately, I think, for deep reasons. I mean, maybe it's one of the mysteries. Different physicists have different views on this, but maybe one of the mysteries is that our universe is mathematics is a guide to the way that the universe works. Eugene Wigner, a very famous physicist, wrote an essay called The Unreasonable Effectiveness of Mathematics in the Physical Sciences. And I think unreasonable is the right word. It's like, why does this thing? There's a quote actually at the start of my show from Paul Dirac, and the great Paul Dirac. And he says that mathematicians search for mathematics that they find interesting. That's what they do, right? They don't care. They just find interesting stuff and do it. But he says, so often it turns out that the mathematics that the mathematician finds interesting is the mathematics nature has chosen. And you go, why is that? That's a deep thing, right? So that's Paul Dirac wondering about this. So we don't have an answer to these questions. I've heard people say, well, perhaps it's because we live in a universe with regularities, because we are complicated things. It's another idea in my show. It's about emergent complexity. I mean, the fact that, as you said in the introduction, 13.8 billion years after the universe was hot and dense, which we could call the Big Bang, although we can talk about that later if you want as well, then these particles that were around and the forces 13.8 billion years ago have assembled themselves into structures like us that can understand the universe. So our universe can understand itself. That means there's regularity in there, and mathematics is the language of regularity and pattern and symmetry. So some people argue that's a reason. So mathematics is the right language because we're talking about regularities. But I've heard other people say, no, I don't know. That's what I like about it. It goes back to what you said in the introduction. It's one of the wonderful things about physics and science in general, all sciences, is that we're trying to understand this deep mystery, which is, first of all, why does anything exist at all? And secondly, why does it exist like this, that collections of atoms can have a conversation? Carl Sagan said it. He said a physicist is a hydrogen atom's way of thinking about hydrogen atoms.
Yeah, exactly.
It's a good thing to be.
And he also describes in the book Cosmos that other living creatures should not look at all like us. He describes as big bubbles of gas that eat all the other bubbles and stuff like that. But
that was those things in Jupiter, wasn't it? He thought about these things floating around in the atmosphere of Jupiter.
Are you thinking about these kind of things? Like, do you imagine how I don't know, you said about this big superconductor. Are you thinking about who is creating that big superconductor? Where is it placed in?
Well, yeah. I mean, who is creating it is the question. Why does anything exist at all? That's which is a good question. I mean, Einstein struggled with this idea. So I mentioned in the show that I think historically it's right to say that Einstein thought maybe the universe was eternal initially. When he wrote down his theory of general relativity, 1915, it very quickly was applied to the universe as a whole. So it is a theory of space, time, but it's a theory that you can apply as a model to the universe.
Yeah.
So you can have a model universe in that theory. And it does strongly suggest, when you do that, just mathematically, that the universe is stretching or shrinking. So the fabric is stretching or shrinking. Either way, if it's stretching, then that implies everything was closer together in the past. If it's always been stretching.
Yeah.
Right? So that means everything's close, which looks like an origin to the universe. And if it's shrinking, of course, it looks like there may be an end. That implies maybe an end to the universe. So either way, I think Einstein's theory, it's quite difficult to have an eternal universe in Einstein's theory. And he didn't like that for the reasons I think we're talking about. If you have an origin, you have to start saying why. What is that thing? What does it mean to have a beginning? And it turned out that experimentally in the 1920s, Edwin Hubble discovered that the universe is expanding. And so that once you've got that measurement, and again, I talk about this in the show, we have those measurements now for thousands and thousands and thousands of galaxies. So we have this whole map of how the universe has changed and evolved over time experimentally. And then with Einstein's theory, you can figure out when everything was on top of each other, which is 13.8 billion years ago. So you have this question of an origin. But just to say, it's not being uncomfortable. It goes back to what you said about being terrified. It's not unnatural to worry about that, what it means to have an origin to the universe, because Einstein didn't like it, right? He was worried about it, although he accepted it ultimately because that's what the evidence tells you. Now, I should say, now that we still don't know what it means, that an origin. An origin in time, was it really the beginning of time? Stephen Hawking and many others have thought about these no boundaries things and all sorts of things where you don't really have an origin in time. We don't actually know what time is. So I tend to say that we don't know space time. We talked about it before, may well come from something else, which is deeper. We don't have the deeper theory yet. We have ideas. It's called quantum gravity. Until we have those deeper theories, then we really talking about the origin of the universe is very difficult. So it's fascinating, and it's current research. So I say in the show, and I say at the end of the show, and it maybe if there's one moral to my live show, it's that we don't know is the most powerful phrase in our language, because what it means if you say we don't know is there's new knowledge to be gained. And if you don't accept that there's new knowledge to be gained, there is no progress. So progress, our civilization rests on people realizing that we do not know everything. Right? It's the most important thing. And it's also very difficult for people. You see it everywhere, right? People don't like to say, I don't know. But there's no science without that.
But you say, we don't know, but then we imagine things and then we test them. Yeah. And then we find out if the test isn't right, the idea is bad. If the test fits in, then the idea is good.
It's Richard Feynman. He said that. And he said it's not even imagine, it's guess. I remember Feynman saying it in a lecture.
Yeah.
He said, we guess, don't laugh. And everyone laughs. And he goes, don't laugh.
So do you guess about things?
Guess.
I mean,
we that's what theoretical physics is, right? You guess. He just said, don't make it any more. You guess about, obviously it's an educated guess, but you make a theory, which is a guess. And then you see what the theory predicts, and then you have to go and test it. And as Feynman very famously said, if your prediction disagrees with experiment, it is wrong, and it doesn't matter who you are or how famous you are or how many titles you have. If your theory disagrees with experiment, it is wrong. And that's it. That's it. That's all. Actually, in the show, so my live show, it starts with Johannes Kepler.
Yeah.
On the Charles Bridge in Prague, 1609, as Kepler wrote, New Year's Eve, 1609. He was walking across the Charles Bridge to a party, and he was looking at the snowflakes landing on his arm. and thinking, asking questions about the snowflakes. Why they're the shape that they are, why they have 6 corners. And he wrote a beautiful book, which you can still get, called The Six-Cornered Snowflake.
Mhm.
And I recommend it very strongly. That book, that time is the beginning of modern science. So you have Kepler, Galileo, it's shortly after Copernicus, just before Newton, decades before Newton. And so that is the moment, really. And it is almost a moment. Many historians would agree. There's obviously things happened before, but it's the time when we started saying we can look at nature. So Kepler was interested in the motion of the planets in the sky, and he figured out around 1610 that the planets move in ellipses around the sun from the data that had been acquired. So it's the time when we start using data to build models of the world. That didn't really happen before around 1600, not in that way, and certainly not in the way that Newton did it in 1687. So that idea that you start out, doesn't matter what you think. I mean, Kepler had all sorts of strange ideas about platonic solids and all these things, and which were really based on Greek ideas. And the cosmology at the time was Aristotle's cosmology, that the Earth is motionless at the center of a finite universe. That all went in a few decades, around 1600, because of observations of nature. So that's a big change. And many historians argue that that's the beginning of the modern world. So it's the beginning of modern science.
They were imagining things that they proved to be wrong, in the end. Do you think we are going to be proved to be wrong right now about things that we know?
Yeah, or not. Wrong is an interesting word, actually, in science. So you could say that Newton's law of gravitation is wrong.
Yeah.
Right. But it's not wrong, actually. It's a good approximation, which is useful in many circumstances. So we're just sitting here now. The Artemis 2 spacecraft has just gone around the moon and landed back on Earth.
Yeah.
That trajectory, which is quite remarkable if you look at it, the way that the moon, have you seen those graphics online where the moon's coming and the spacecraft goes around and comes back, and it landed within about a mile, I think, of where it was supposed to land in the Pacific Ocean. That's Newton's laws that are used to do that.
Yeah.
You don't need relativity. So you don't need the more complex model. So I think the way I would say it is that we have models of the way the world works. One of the great leaps, actually, in this around 1600 was to start thinking about our models more than just calculational things. Because you have all these epicycles and everything, right? You can calculate the solar eclipses and things like that without knowing that the Earth goes around the sun, right? They were calculated and they work. But there's something elegant about this model of the elliptical orbits. And so the point is that, so are Newton's laws wrong? Yeah, we have a better model now, which is Einstein's theory of general relativity. Is that absolutely right? No, it fails. It tells you where it fails. It fails in the singularity in black holes. It fails at the origin of the universe, if there is such a thing. So it doesn't work in all circumstances either. Is it wrong? No, it's just a model. So we have this idea of what we call effective theories now, effective field theories and things. So I would say wrong. But anyway, wrong. It is wrong. A model is wrong, yes, when it makes a prediction that disagrees with the experiment. But Newton's laws predict the wrong orbit for Mercury around the sun. They do not explain the orbit of Mercury. Einstein's theory of general relativity does explain the orbit of Mercury. So it's a better model.
So we are getting closer and closer and closer.
Well, yeah, or are we? Then again, that would be an assumption, wouldn't it? It could be that, we don't know what we don't know. You often hear a theory of everything, right? As people say, the theory of everything. Wouldn't it be great if we had the theory of everything? We don't actually know whether there's a theory of everything, right? Some really beautiful thing you can write down on one page of paper that explains everything. Our experience in the 20th and 21st century is maybe there is such a thing. We have an experience of writing down simpler and simpler and more elegant equations that describe more and more.
The standard model.
But it could be that whatever this deep theory of quantum gravity is completely, it's completely beyond us. It could be a total mess. Who knows, right? But so I think that the reason I make this point is because I think humility is central to science. So, and I often make the point actually in that you don't set out to, Feynman said this as well, you don't set out with a grand vision, like I am going to explain how the universe began. You don't really get anywhere if you do that actually. What you do in science is you set out like Kepler did or Newton did to say, how are those points of light moving in the sky? What's a good explanation? Are they going like, and Kepler said, well, they're going in ellipses around the sun, which is radical at the time. Right?
Yeah.
People were still arguing that everything goes around the earth. And he said, no, the data's better explained if they're going around the sun in an ellipse. Right? And then Newton comes up with a model, which is there's a force, and he tells you how you can work out the force. And that's good. So there's a humility to it in that you're not trying to do anything other than explain how those points of light are moving. You're not, I mean, it turns out that the theory of gravity, Einstein's theory of gravity that replaces Newton's, or is a better model, then starts telling you about the universe as a whole and suggests the universe had a beginning. But you didn't start out saying, if I find a theory of gravity, I will be able to explain why everything exists.
Yeah.
You'll get nowhere. If your goal is to understand everything,
you're
going to understand nothing, I would say. So you've got to understand little things. And then sometimes that allows you to ask bigger questions.
Let's talk about how we are made, okay? Because there are stuff that we already know, I presume, like how the mass was formed, and how all of these molecules are formed. And you call that, and Carl Sagan calls it stardust.
Yeah, star stuff.
But why do you call it dust? Because like dust is something like disposable, like it's a disposal from a star. But actually, like the carbon molecules and steel molecules are made in the center of the star in a big pressure and big temperature. Yeah. So we have the iron molecule in our blood, and the only way the iron is formed is in the center of the star. Yeah. So I have inside of me molecules from the center of another star.
Yeah. So close to the Big Bang, in the first few minutes in the history of the universe, hydrogen and helium are formed. Very famously, 75% hydrogen, 25% helium, which is a prediction of the Big Bang model, actually, which was subsequently verified. Yeah. So what you have is hydrogen and helium, tiny bit of lithium.
That's all, right? In all in your
That's
universe.
it. So that's all there was, right? So basically hydrogen and helium and a little bit of lithium. And I think a tiny bit of beryllium as well. So there's the really light ones, right?
So it's like a soup, like a big soup.
Yeah. Well, very similar to a soup. It's just nothing. It's just gas, right?
Yeah.
And dark matter, which we can talk about a bit later on. But anyway, so then carbon does not exist. There isn't any carbon for the first few, well, I'd say 100 million years or so in the life of the universe or more. There's no oxygen, there's no iron, as you said. So where does it come from? This was a big question, by the way, in the 1920s and 30s and 40s. It was cutting edge physics. It turns out that we now understand that those heavier elements are made in stars. So you're right, that's where they come from. There isn't any after the Big Bang, and there isn't any carbon or oxygen or iron until generations of stars have lived and died. And that's where it gets made. So so that's what Carl Sagan meant. We are star stuff, or star dust, as he used to say. And it's true, apart from the hydrogen, which is, although that will have probably gone through, maybe it's been part of a star at some point. So other than the hydrogen in your water molecules, you are made of star stuff, right, basically. But that, actually, the heavier stuff is still really cutting edge research where that comes from. So gold, for example.
Yeah.
So gold was quite a mystery. And then a few years ago, we saw through these things called gravitational wave experiments, which are ripples in the fabric of the universe. And famously, we see those from colliding black holes, for example. but we saw some of those ripples from the collision of neutron stars, which are these stars that are not quite massive enough to collapse to form a black hole. So they form like almost a single atomic nucleus. And they're very ultra dense. When they spin and give out radio waves, they're called pulsars, right? So these things. And so we saw a collision of two of those in the gravitational waves, and we got our telescopes and spun them around to look at that region in the sky where this collision had come from. Is a collision of neutron stars, and we saw gold being made in that collision. So we observed it.
Yeah. Okay.
So we know that at least some of the gold, and I think most of it, I think is the current view, is made in collisions like that. So then it's even more interesting if you've got a gold ring on now or whatever, your wedding ring, that thing, at least probably most of that, if not all of it, got made in the collision between neutron stars.
That's kind of romantic, yeah?
So it's amazing. So the story of the origin of the heavy elements is a remarkable story.
But what about diamonds?
So they're carbon. So you make the carbon in stars, and then you have to compress it to really heavy, high pressures and temperatures, which get made in the earth.
Gold is kind of more interesting, than diamonds.
Oh, yeah. There's loads of carbon around. There's very little gold because it was made... primarily we think in the collision between neutron stars.
So these neutron stars, how I understood it from your book.
We didn't know it when I wrote that book. So this is a recent discovery, that one. So I think if you go back to 20 years or so, there's a lot of theoretical work done. And so people used to talk about it being made in supernova explosions, which is, I think, also possible. I don't actually know the current state of the art. So, but I think it used to be, if this was 20 years ago, most people would have said, it's supernova explosions, we think. We're not quite sure, but this observation showed it being made in the collision between neutron stars. So.
But you explain what is a neutron star here in the book, and you explain what is the pulsar. We should not go into details, but what I understood is that when you have a very big star and it has big temperature inside, it goes out of the fuel, it contracts, it gets another fuel by contractions, stuff like that. Yeah. And if it's too big, it becomes this neutron star, and it's very dense. The pulsar, it's very dense. It's heavier than our sun, but it's 20 kilometer diameter. Yeah. And it's moving very fast. And
they spin.
They spin, So they spin. So ultimately, they can create the black hole.
No? So there are different... so if you think about what a star's doing, so gravity's trying to collapse everything, right? Gravity just as attractive force, it squashes things. So if you've got a planet or a star, or something's got to stop the collapse.
Yeah.
Right? So in a star, it's the nuclear fusion reactions in the core.
Yeah.
So hydrogen gets turned into helium in a star like the sun. That releases energy, E equals mc squared, which creates a pressure, a temperature and a pressure which holds the star up.
Yeah.
So it's balancing. So the gravity is trying to squash it. The heat, essentially the energy from the reactions, holding it up, and it's there. Then it runs out of fuel, and which it will. And our sun is burning 600 million tons of hydrogen into helium every second.
Okay.
So that's quite a lot. So it's got another 4 or 5 billion years to go, and then it will stop. Then it'll collapse again. And gravity. So then the question is, what stops it then? Something else has to stop it. So there are different stages. It depends on the mass. So there's a stage called a white dwarf star, which is what our sun will become. And the thing that stops that is a really interesting thing. It was first calculated by Chandrasekhar in I think it was 1930s, the calculation. But it's so what happens is it collapses, and the electrons in the atoms in the star. So there's a thing called the uncertainty principle in quantum mechanics, which says that you can't, if you try to confine something, the speed, the momentum gets uncertain, and it starts jiggling around more. So the more you try and confine a particle, the more it jiggles. And so that makes a pressure, right? Because you're squashing everything down. So these things are jiggling around, and that's enough to hold the star up to a certain limit, called the Chandrasekhar limit, which is actually 1.4 times the mass of the sun, right?
Okay.
So white dwarf star, that would be a star the size of the Earth, with the mass of the sun. and it's held up by these electrons jiggling around. And actually, there's a book I wrote called The Quantum Universe after that one, where we do that calculation in the book, myself and Jeff Forshaw. So you can do the calculation and figure out the Chandrasekhar limit. It's really cool. So that's fine. But then that can go wrong. If you've got too much mass, because one way to think about it is the electrons can't jiggle around faster than the speed of light. The speed of light's a limit.
Yeah.
So they basically give up and it collapses again. And the electrons collapse onto protons and make neutrons. And then the neutrons can jiggle around. So a neutron star is held up by the neutrons doing the same thing.
Yeah.
And that can hold up more mass. And then you get the star, you said, the size of a city, 20 kilometers across, held up by the neutrons. It's called neutron degeneracy pressure, if you want to know, and jiggling around. But there's a limit to that as well. That's not infinite.
Mm-hmm.
And so if you go over that limit, then you go to a black hole. That means nothing stops it collapsing. So there is no process that can stop it collapsing under its own gravity.
So it continues to collapse.
So it just collapses basically out of existence. So this is
what is that? How can we understand that?
So a black hole, this is what a black hole is. So it's something that nothing can stop the collapse that we know of. So it collapses to a point where space and time are so distorted. Remember, that's what gravity is in Einstein's picture. It is the distortion of space and time, right? So space and time are so distorted that essentially you get this distortion. It's like a black hole is like an imprint in the fabric of the universe, a distortion in space and time, and really nothing else. So really Einstein's description of a black hole is that it's almost as if you've removed the star from the universe but left its imprint behind. Now, it might sound odd that, so you go, what does it collapse to?
Yeah.
And so we call it a singularity. So in Einstein's theory, the theory gives up at that point. It says it will collapse without limit. Nothing will stop it. And it collapses to what we call a space-time singularity. Now, what is that thing? So in Einstein's theory, if you look at the thing from outside, you look at the description of the black hole, that is actually a moment in time. It's actually the end of time. So just technically speaking, in Einstein's theory, the singularity represents the end of time. So you fall into a black hole, you cross what's called the horizon of the black hole.
What happens? Let's imagine, let's go with imagination. Yeah. We don't know for sure, but imagine that you fall with a spaceship into the black hole.
Yeah.
What happens?
So for a sufficiently massive black hole, so let's say the one at the center of the Milky Way galaxy.
We have one in the center of the Milky Way.
That's about 6 million times the mass of the sun, that one. There are black holes that are billions of times the mass of the sun.
When you say these numbers, do you understand them? I mean, you try to imagine them or you just give up?
No, I mean, these supermassive black holes are just unimaginably violent objects. But I'll give you so for a sufficiently massive black hole, the caveat I'll explain in a moment. But for a big one, you can, as far as we understand it, according to Einstein's theory, you can fall across the horizon of the black hole into the interior and not notice. So you will not feel anything, and there's no measurement you can do in a small region of space like this room for a big black hole that would tell you that you were falling across the horizon. So we could be falling across the horizon now into a supermassive black hole, and certainly according to Einstein's theory, you wouldn't notice. What you would as you go towards the singularity, which is precisely defined, it's the end of time in Einstein's theory. So you basically, what we would feel is time would end ultimately, and it's about, if I remember rightly, for the really big supermassive black holes, you have about a day or so, a few hours across the horizon. Nothing much happens. Really close to the end of time, you feel what's called tidal effects.
What is that?
Which you get, so tides. So it's like the tides on the Earth, right? But a much more extreme version. So you get stretched. There's a difference in the force, basically. You get stretched in one direction and squashed in the other direction. So you get, there's a word, people say spaghettified, right? Where you get turned into spaghetti.
That's the spaghetti effect, yeah.
That's spaghetti, yes, that's tides. So the reason, as an aside, the reason I said big black hole is for little black holes, you feel the tides close to the horizon.
Mm-hmm.
So, but for big black holes, it's kind of forget that. For really big black holes, you don't. So you go across the horizon into the interior. Eventually, you feel the tides, and then time ends. And then this is the singularity. Now, you might ask the question, what is that thing? And the answer is we don't know what the singularity is really. Well, not even really. We don't know what the singularity is.
Right now, we could fall into a black hole, and we would not notice it.
No.
But could we still speak like one to each other
while
falling?
There's a thing. So one of the central ideas, which is that in Einstein's theory of gravity, it's called the equivalence principle. And it's actually the initial idea he had, that he said was the happiest thought of his life, which is if you're freely falling. So think of an astronaut on the space station, for example.
Yeah.
What is the space station doing? It's just falling, freely falling in space.
Yeah.
So there's no... So that is, nothing is happening there, right? There are no forces acting on you. That's why in free fall, if I let go of that and I was on the space station, it would stay there.
Yeah.
Right. Why? Because you're in free fall. There's no experiment I can do to tell me whether I'm freely falling in the vicinity of a planet or I'm floating between the stars. Right. So the equivalence principle essentially was this happiest thought of Einstein's life. It was the key to his theory that when you're in free fall, if you're in a box and you can't look outside, you don't know what's happening. You can't make any measurements inside that tell you whether you're falling towards a planet, falling across the horizon of a black hole, or floating between the galaxies, right?
But what does it mean that the time stops? Like, can you still exist if the time stops? Because we are existing in this space and time.
No, I mean, that's the end of time. So it is the
end
like
of
time. Well, yeah, I guess. I mean, it's just in Einstein's theory, you can draw it on a map and you just get an end. It's like the edge of this table. So it's like, let's say time's going up there towards the end of the table. There's just an edge, and that's the singularity in the black hole. So you draw this map, it's called a Penrose diagram, and you see this edge, and it's just end of time. End. So time ends in there. So that is the Einstein picture of a black hole. Now, what's very cool about black holes now and really interesting is everything I've said there is Einstein's theory, Einstein's picture. And this was figured out by Carl Schwarzschild and others. He didn't know it at the time, but in 1915 or 1916, shortly after the theory was published. So it's all there. And it's mathematics you can learn as an undergraduate, right? But now, though, after Stephen Hawking in the 1970s, we start to involve quantum mechanics in the black hole, and we start to say what happens. And the reason I was slightly careful with what happens on the horizon is that Stephen calculated that the horizon of the black hole, I should say what it is, the horizon. So I said you can just fall through it for a big black hole. So it's nothing, right? It's nothing. It's just space, except that once you're across it, you are going to the end of time.
Yeah.
Nothing's coming out. A good way of thinking about why people often say you are going to the singularity, right? Why do you have to go to the singularity? Where do I have to go to this place? You might be tempted to say. If you think of it as the end of time in your future, it's pretty obvious why you have to go there. It's the same reason you have to go to tomorrow.
You cannot go back. Okay.
You are going to tomorrow. Right? We are going to tomorrow. So it's tomorrow.
You cannot go back to yesterday.
No, you can't. So it's tomorrow. So tomorrow is in your future. Okay. And tomorrow is where time ends until you go there. And that's it. So, but Stephen Hawking discovered the initial calculation he did, 1973, 1974, is that the horizon, let's say, put it this way, it disrupts space such that particles come off. It has a temperature. So it's called Hawking radiation. So he calculated the temperature of a black hole, which is now on the floor of Westminster Abbey in London. On his gravestone is his equation for the temperature of a black hole. So it's really important. So that means that black holes have a lifetime. They don't live forever in that picture. They one day they'll be gone. What? So because they evaporate. because they're hot, so they glow, so they emit particles and they shrink. So that's led to all sorts of problems in the black hole information paradox and all sorts of things. So we don't really know what happens at the end of a black hole's life. Some people still think that maybe there's some kind of remnant left over, that somehow there's another universe that almost sort of gets pinched off inside the black hole, which is where all the information goes. Or many people think that's not true, and the thing just goes, and you just get the Hawking radiation, just radiation left over, and all the information about stuff that's gone in is in the radiation. This is a live area of research, so it's we could talk about it forever. It's really cool. The ultimate answer is nobody knows what happens, but this is all. So every time we talk about these things, we have to be clear that we don't. There are images. There are pictures where you could fall into. If I watch you fall into a black hole, for example, now, and it's over there, then I would not. It's true that I would not see you go in.
Yeah.
So I would see, for you, time slow down from my perspective, and I would see the time formally freeze on the horizon. So I wouldn't see you go in. From your perspective, you'd go in. Yeah. So you would have no problem. Time goes at 1 second per second, free fall, the equivalence principle. Everything's the same.
So that's why we cannot see black hole. They're black because nothing comes out of it.
Nothing comes out, well, except that they glow with this very low temperature of Hawking radiation. We do see them because we see the material orbiting around them. So in Interstellar, for example, that picture of a black hole, that's a simulation of a black hole using Einstein's theory. And so that's material orbiting around it, glowing hot. That's how we see them. So we have a photograph, the Event Horizon Telescope, of the M87 black hole, a very famous photograph, which was the first photograph taken of a black hole by radio telescopes. And
what do you feel when you watch all of those telescope pictures? What do you think about? What do you feel? Do you feel? Are you afraid of?
No, I mean, in the live show, I show some, images, some simulations of, let's say, visualizations of data of the universe on the largest scales. And I say to the audience, it's obviously it's terrifying at some level, but it's the way that nature is. And you need all that stuff, by the way. You need all those galaxies. You need a universe of this scale and size, and the stars, as you said earlier. You need all that to exist. So you're in a sense being terrified of your own history. It's your own necessary history. So you shouldn't be terrified of the processes that led to your existence, I would say. But that's where the reason I have some music in the show is because ultimately there's some Mahler in the show. I like Mahler, and Mahler once was asked, what are you trying to say with your music? And he said, if I could say it, I wouldn't write the music. So there's some, I think that there are feelings, as you say, that arise when you think about the violence and scale of the universe that you can explore, and you can explore them through music or art or philosophy or whichever way you want to explore them. But ultimately, that is the reality that allowed us to exist in the first place. So I wouldn't be frightened of it.
Yeah, were you afraid of it, like in the past, and how did you overcome that? Like, I mean, like I'm curious, what was the most the moment you were like in awe of finding something that changed you?
I've always liked astronomy, and I've always found it intriguing and fascinating that these things that you see in the night sky are suns, and then you hear about how big some of them are, like in Orion, the star Betelgeuse or Betelgeuse, however you want to pronounce this thing. No one knows how to pronounce it as far as I know. But that's a red giant star. And if you put it where the sun is, it would be, I think it would engulf Jupiter, right? You go out to Jupiter's orbit, these huge stars. But I've always found those just fascinating because it's the way that nature is. The astonishing thing to me is that there are places in this violent universe which are so gentle that things like us can emerge on them. I say that in the show, it's 4 billion years it took from the origin of life to a civilization on this planet. And for some astonishing piece of luck, nothing bad happened to the Earth for 4 billion years. so that life.
It's hard to believe. Yeah, if you would say the tale, it would be hard to believe.
Yeah, which is probably my guess for why we don't see evidence of other civilizations nearby.
Do you think there are other civilizations? Like, just a guess. I know you're like, we don't know, but do you think there are other civilizations?
In the universe, I'd say, yeah. I mean, there are 2 trillion galaxies in the observable universe, and the universe goes beyond that edge that we can observe. So I would be astonished if there aren't other civilizations somewhere. The real question is, how close are they?
Yeah.
That's what matters to us, really. How are they contactable? And my guess would be not. So my guess would be that there are very few or maybe no other civilizations currently in the Milky Way galaxy, I would guess. That's a guess, right?
Yeah.
I'd love to be shown that my guess was wrong. And I always say that I wouldn't be surprised. If you open that window now and there was like a UFO landed outside, I wouldn't actually be surprised.
You would say, finally.
Yeah, I would say, oh, good, that solves a problem that I've worried about for a long time, which is, where are they? It's called the Fermi paradox, right? Yeah. And I worry about that. We think about that. A lot of people think very carefully about why it is that we don't see any evidence of other civilizations. And it's quite hard to figure out why. My guess is that it's the time that it takes to evolve. So, as I said, on Earth, 1/3 of the age of the universe is what it took for us to evolve. And that is a long time. Many stars don't live that long, right? So I just thought, okay, that maybe that's it. But it's still kind of difficult to think about. There are a lot of planets. There are maybe 10 billion or potentially Earth-like worlds in the Milky Way galaxy, we estimate. And there's been a lot of time. So surely someone should have become a spacefaring civilization, you might think, and they should be around and we don't see them. That's the Fermi paradox. Paradox is a good word. So I think at the moment we don't see any evidence for them. That's a puzzle. And so maybe it's biology. That would be my guess. It's just a long time that it takes to make complex organisms. But if one landed outside now, I'd be like, oh, actually I'd be relieved, to be honest. I'd be like that answers my thing. My question has now been answered. Mm-hmm. There are other civilizations out there. And also, it's not all down to us. Yeah. Because I'm worried that if we mess this up, then there's nobody else in the vicinity, by which I might mean the galaxy, to bring meaning to an otherwise meaningless universe, I would say. So therefore, if someone lands outside, I'd be like, oh, good. At least there's somebody else. So let's rest now. If we mess this up, it's not so bad.
Yeah, because
I would think that's
because like I started this podcast saying that you have this feeling that you're so small and insignificant. Like if we vanish, universe probably won't care. But then if we are alone here, we have like a mission maybe, and we don't have to mess up. Yeah,
and that's my position.
You think we're messing it up? Like watching what happens in the world and in history?
Well, we've not messed it up in the sense that we're still here.
Yeah.
But we've only had the power to destroy ourselves.
Yeah.
For, let's say, since 1945, right, with the atom bomb. Let's say.
Yeah.
So we've only had the power to destroy ourselves for 80 years, and we haven't done it. So whether we're messed up or not, the who knows? And now we're coming across ever more effective ways of destroying ourselves. So now we don't only have the nuclear weapons, we might have, I don't know whether AI is going to be a threat to us or not.
You think so?
It will be a useful tool, undoubtedly. I don't know whether it will be a threat. Some people think it will be a threat. So, but we're probably coming across more ways, bioengineering and things like that. Maybe we could build bioweapons. Who knows, right? So we're getting better and better at inventing ways of destroying ourselves. So I'm not entirely convinced that we won't, but we've avoided it for 80 years or so since we gained the power to destroy ourselves. So maybe we won't.
And I think that's why, sensible. That's why astronomy is so nice, because it's not just theoretical. When you see like this mission, Artemis 2 mission, and you see people going to the space, it makes you feel about us that we are united in this mission all together.
Yeah, I think it's one of the great benefits of perspective. That's what Carl Sagan said, that, you know, and in my live show, I do have a shot of the pale blue dot image, which is the famous photograph of Earth that Voyager 1 took from beyond the orbit of Neptune. And he wrote very famously, if you haven't heard it, I'd strongly recommend it. He wrote the pale blue dot piece, which is beautiful, where he says that imagine all the, I can't remember what the exact words were, imagine all the rivers of blood and the generals and the kings and who fought over the momentary possession of a fraction of a dot.
Yeah.
And it's a beautiful piece of writing, and it's about perspective. And ultimately, I think one of the most valuable things that astronomy gives us is perspective. It tells us that we are one planet around one star amongst 400 billion stars in one galaxy amongst 2 trillion galaxies in the observable universe. That is what we are. But it may also tell us that we're remarkably valuable because this planet might be one of the few places where collections of atoms can have a conversation like this. And so that's why I love Cosmos. To get back to the end, to that place we started, that's why Cosmos is such a brilliant book. Because Carl Sagan, for me at least, is the first time that I saw someone who is an astronomer and a scientist talking in that way. So saying, what does it also mean for the way that we behave and the wider culture and the way that we behave as a species on this planet? And that for me is the power of Carl Sagan.
And you're continuing this legacy, and with all you do, all of your materials, the TV series, the books, and the Emergence, this tour that you're in. We're now in Copenhagen. I hope like in the morning I send the newsletter. We have a newsletter, and I send the newsletter, and I said in the newsletter, if I'm lucky, and I didn't know how I will make it, I will get a ticket from you to your tour.
I just assumed it.
Yeah. And your colleague came, and she was like, and what you doing today? You're living back home? And I said, like, it depends. And it depends on what? It depends if you're going to give me a ticket or not.
Of course, we're going to give you a ticket.
So we got two tickets, me and Mihai, the owner of the studio here in Copenhagen. Yeah. So I'm going to see the show. But for the people and it's very important to know that you are coming 22 September, you're coming to Bucharest. Yeah. So people in Bucharest can see you in Bucharest and your Emergence show. What can we see there?
Oh, so it starts with the story of Kepler and his snowflake, which is what I talked about earlier. This wonderful moment, one of the beginnings of modern science, when Kepler thinks about the symmetry of a snowflake. And then it goes on to talk about what we've learned about the size and scale of the universe, but also these questions we've been talking about life in the universe, the emergence of life, how common is life in the universe. There's a lot of music in there. So in the start of Act 2, so one of my favorite artists is PJ Harvey. So you know PJ Harvey's a great musician. So she came to one of my shows on the last tour, and we got talking and we became friends, and she's interested in many of the things that I am. Nice. So I said to her, do you want to write some music? And she said, yeah, okay, I do. So she sent me lots of things, and we ended up coming up with this song that is about Voyager, the Voyager spacecraft, which I mentioned earlier, the pale blue dot image. Looking back at Earth, it's 50 years that these spacecraft have been in space. Next year. They were launched in 1977, these things, and we're still in touch with them. They're in interstellar space. And I had this idea that maybe what would they say to us after 50 years in space, going past all these planets and looking back at the Earth. So she wrote this incredible, beautiful song that we recorded recently at Miraval Studios in France. And so that's at the start of Act 2. And so it tells the story of Voyager, talks about life in the universe, talks about multiverses, it talks about the origin, the laws of nature, all sorts of sort of ideas. The Higgs particle, I talk about that as well. And then the end is about some of the themes we've talked about what science can teach us and how we've learned these things and how we can use that to have a safe and more prosperous future. And the music for that was written by a friend of mine called Dario Marinelli, who is a great, famous movie composer who has an Oscar. And Dario I asked him, I bumped into him randomly in Iceland, believe it or not, in northern Iceland, and said to him, "Oh, do you want to write some music?" And he said, "Yeah, I'm only doing 4 movies at the moment, so I've got some time, I'll do it." And so he wrote the end music, which we recorded with an orchestra. So that's in at the end. So you'll see there's a lot, as well as the science and the cosmology, there's a bit of black holes, multiverses, quantum mechanics, all that stuff. There's also this thread of the things we've talked about the importance of acquiring knowledge about the world, the importance of not knowing, and they all come together with all this new music and the biggest LED screens we can fit in quite a big venue, actually. In Bucharest.
And we can see all this astrology stuff,
all the astronomy, new images. Yeah, don't say astrology. New images of James Webb Space Telescope. We have live images from space with a company that I've been working with called CERN. So we have live images of the Earth from space, all sorts of things.
But you have nothing about astrology, right?
No.
How can you describe astrology? Because
my hero, one of my heroes, who you might not know, but there was a presenter of astronomy called Sir Patrick Moore, and I grew up with him. And he presented astronomy on the BBC for decades, right? And he said once, he was asked about astrology, and he said, "You know what it proves? It proves that there is one born every minute." And that's an English phrase, which means there's what does it mean? It means that there are people born all the time, and they believe all sorts of things.
Yeah,
that's my statement on astrology. Okay. There are people born all the time, and they believe all sorts of stuff.
In Romania, we have a lot of astrology, even at the news. So we have the news, we have the weather, and then we have astrology.
Well, let me put it not in a nice way, right? So it's one of those things. It is the foundation. It was one of the early, looking at these things, it's about wondering about the sky, right? So you see patterns in the sky, and you see these things that we now know are planets moving around, but we didn't know at the time, and these wandering stars that move about. And so noticing the heavens and thinking about it, and thinking about how the heavens interact with us on Earth and how we come from them. We now know we come from the heavens, as we talked about.
Yeah.
That's history. It's part of history. So I would say that it's a part of history where people are wondering about their place in the universe and how they fit into the universe, right? We now know that the motion of the planets against the stars doesn't have any effect on it. We know that now, right?
So we know that.
So yeah, but I'm always careful to. I don't want to. Carl Sagan said it right in that there's a book he wrote called The Demon Haunted World, which I strongly recommend. And he wrote it after Cosmos.
Okay.
Science as a Candle in the Dark. And in that book, in the first chapter, he tells a story of it being in a cab in New York City with a cab driver. And he was famous at the time, Sagan, this famous astronomer. And the cab driver kept saying to him, you're the astronomer, right? So you know about all these things. So what about Atlantis? Do you think about? And Carl Sagan said, "No, I don't think there's a city called Atlantis." He said, "What about UFOs?" He said, "I don't think there's UFOs landed on." And what about this? But Sagan very wisely said that he didn't just think, "Oh, this guy, he believes all this stuff." He thought, here is someone who is interested in the world, and he's asking interesting questions about the world. He's asking questions about alien life and questions about whether there were ancient civilizations on Earth and how they were. So Sagan said that the thing to do is to take that wonder, right? The fact that people are noticing there's something interesting and mysterious and beautiful about the world, and then use it. Don't say, well, the things you believe are nonsense, but use the wonder to say there are mysteries here, and we can talk about the deep mysteries, right? And as Sagan always said, the fact that it's so much more wonderful than that, right? It's not that you just points. It's not just there are constellations, and there's this constellation called Pisces or whatever it is, and there's this pattern of things. Those things are stars. And around those stars are planets. And so they're all solar systems, those things. And they're thousands of light years away, some of them, hundreds or thousands of light years away. And there are worlds there, and we could explore those worlds. And then there's the story you said of the 13.8 billion years, and once it was just hydrogen and helium, and the building blocks of us were made in those things in the sky. And so the fact is that what you want to do is capture people's sense of wonder, and then say, these are the things that we've learned. This is our picture of the world now, which is actually more astounding and beautiful than the world that we saw in the medieval world or something, when we didn't know anything about the world. The more we've learned about the universe, the more astonishing and wonderful it is. And so astrology is part of that history of astronomy, but we've learned a lot more since then.
Yeah, so if you're curious about astrology and you watch Astrology of the News, you can come to Emergence show and see, you can use that curiosity, because it's not like, the curiosity is good, but it's not true. Yeah, what? Well,
I could say, because we now know what those things are.
How do you usually? I mean, I love how you explain how you. And this is like my last questions, because our time run out. But how do you fight pseudoscience? Because like in Romania and probably all over the world, we have right now quantum healing and quantum healers and quantum psychology, and everything is quantum. I mean, every pseudoscientist that wants to sell you something, it uses quantum inside the quantum something.
Well, following Carl Sagan with astrology and astronomy, what you would say is, so you're interested in quantum mechanics? Well, there you go. This is quantum mechanics. It's great. Yeah. So that's what I would do. Use it as a way in. I talk about quantum mechanics at the show. So if you want to know a bit about quantum mechanics, come to the show and
you have quantum healing?
No, but quantum mechanics lies at the heart of transistors.
Okay.
So the phone that people are using to watch the stuff about quantum healing operates on the principles of quantum mechanics.
Really?
That's how transistors work, right? And so actually, it's more amazing. That stuff, just forget that. This is the real stuff. You know, the fact that the description of an electron, I say it in the show, an electron in this room. What's the description of it? It's like a thing. It's not like a point-like object, like a grain of sand. It's like a thing that fills the room. It's like a weird thing. So, and we call this a wave function, and it's something to do with probability of finding the thing somewhere. But there are different interpretations of that, and we don't fully understand the theory. But it does work, because your phone wouldn't work if we didn't understand quantum mechanics. So it's very cool. And then there's quantum computers, which we're beginning to develop now, which are potentially very powerful things. And there's quantum teleportation, which is teleportation. It actually works, with photons at least as well. And so that's what I would do. I would say, okay, let's keep the quantum bit, forget the rest, and come and learn about quantum mechanics.
I need to be honest, because like we've filmed more than 100 podcasts, and this one is the one that left me with so many questions. And there's
we've done one question.
10,000 more questions, more than I think it is. And there's no way to fill them all inside.
What we should do is we should do it again in Bucharest.
Yeah, that would be amazing.
Yeah.
So
why don't we do that?
Thank you for saying that. I would wait for a little bit of time, and we'll propose that to you later. But if you say that now, that's amazing. Yeah. So if you have time in Bucharest,
I said it on air.
Amazing. Amazing. We have a nice studio. We're gonna welcome you there with new questions, and some of them arise now. So, Brian, thank you so much. Yeah, thank you so much for accepting this podcast and coming to this podcast. And if you're watching now, and if there's stuff you didn't understand, you have another questions, then probably like the show will be we'll have some answers to your questions. So yeah, thank you again for all your work, for sparking this curiosity in people, and for like teaching us to not be afraid of physics. I really hate now that I didn't love physics in high school. Yeah, I should love it, but I love it now for sure. And yeah, thank you so much for bringing this curiosity in the mainstream.
Thank you.
Mulțumesc și ție că ai fost până acum cu noi. A fost ca o călătorie în spațiu, nu? Dacă n-ai înțeles lucrurile din podcastul ăsta, e absolut normal. Și eu după ce am citit și m-am pregătit pentru acest podcast, efectiv am înțeles puține lucruri, dar cele pe care nu le înțelegi îți strânesc acea curiozitate, nu-i așa? O să pun link pentru această carte în descrierea acestui podcast, o să pun link către show-ul Emergence pe care o să-l vezi în București pe 22 septembrie și o să pun link către cartea Cosmos de Carl Sagan, care e o carte incredibilă care te învață cum a început viața și cum a început prin evoluție, cum am ajuns noi să fim noi cine suntem. Da, mulțumesc pentru atenție, mulțumesc Unicredit Bank pentru faptul că sprijină acest podcast și lasă-mi comentariul tău în secțiunea de comentarii. Mersi, ceau, pe curând!